welcome. So the title of this talk is Sustainable Testing, and I have these slides available on gitpitch /potato salad/ElixirConf 2018. There's also a GitHub repo that has all the examples that I'm going to describe, plus some more, and links to references and things like that. And so my name is Andrew Bennett. I'm known as Potato Salad on GitHub. And I work for Toyota Connected in the Dallas-Fort Worth area of Texas. And there are actually several of us here at the conference. Matthew Gardner gave a talk yesterday here about machine learning, and Gerald Unruh will be speaking later this afternoon about development and deployment beyond Hello World. And we are hiring for an office that we're opening in the UK. So if you or anyone you know is interested in the London area, let us know. So I gave a talk last year about well-behaved native implemented functions, or NIFs. And I felt like since I chose such a dry and kind of uncontroversial topic last year, I decided to choose a topic that I'm sure nobody has any strong opinions about. During the research for this talk, I found that that there are many developers and managers out there who are very protective about their testing practices, and it kind of causes people who disagree, who have alternate opinions, to feel like they have unpopular opinions. Like this one, it's okay to write tests to help flesh out implementation, and then delete those tests before you merge into master. So if depending on your interpretation of TDD, this may be heresy to you, or I personally kind of agree with this. I feel that TDD is test-driven development and not test-driven testing. So, and I was also pleased to see that one of my coworkers, Gerald, who's speaking this afternoon, mentioned that tests themselves or code must be maintained. There is, the test suite itself is a code base of its own. It has its own kind of life. And so even though the title of my talk is Sustainable Testing, depending on your opinions, the original title of my talk was rejected. So I apologize beforehand. So, just in general, I feel, as the Elixir community, that we need to do a better job at helping, especially those new to the community, or we need to help them be better at testing their software and at improving the quality of the software that they write. There are other communities out there who are doing a better job at this than we are, and I feel like we should learn from them. So some of the symptoms, and there are more than the ones I'm going to list here, but some of the symptoms of unsustainable testing practices might be where a small code change in the system code base results in nearly every test case failing. I'm sure some of you have seen situations like this, where bugs are rarely ever discovered before they hit production, and that non-critical systems are over-tested, where systems that or subsystems that are very, very low on the value scale to the customer have equal priority with the critical subsystems that are, anyway. Hopefully that makes sense. You'll know it when you see it. You know these symptoms when you see them in a test code base. And in general, when you ask people about how they feel about their testing, they're unhappy. They don't like the way they don't trust it, or they don't. It's just a mess. It feels like a giant mess. And part of this is because I feel like as developers we have a tendency to focus on testing implementation details instead of the system functionality. And implementation details themselves change quite often, but test suites are meant to be long-lived. So something that you maybe whip together really quickly as a test today may still be there in 5 to 10 years from now, depending on the life, how long this product might live. And it makes it difficult for other developers to be able to understand whether that test is important or not. Are they allowed to delete it? Does it still matter anymore? And so, anyway, and so I wanted to talk about the reason why we test. And so, did a bunch of research and looked at some really old papers and tried to figure out what the original purposes were behind doing these things. And I feel like a lot of us might say that it's to help protect against regressions, or to prove that a program is correct. But there's a problem with this. There's a whole field of mathematics study and computer science study that shows that you can't do this, You can't prove that a program is correct through testing. Bugs are subjective. They have to be determined by humans at the end of the day. And so, anyway, there's a whole bunch of links there to all the proofs and whatnot. Now, there is an area of study called formal verification that exists, which, to help verify, algorithms formally, but it's very different from what I think we would consider software testing. And so if it's not to prove that a program is correct, why are we testing? Or what's our goal or our objective? It's to find bugs. That should be the main thing that we're focusing on. A successful test suite is one that reveals a bug. And so if a test suite results in just, okay, or you run it and it just says, great, everything passed, you don't know anything new that you didn't know before. And so some of the techniques that are out there for finding bugs include test-driven development that kind of helps during the development process to help you find bugs while you're developing. There's things like acceptance testing where you write tests based on more of the consumer or the client side view of things. And there's focusing on things like code coverage and that. And there's model checking and kind of the subset of that, which is property-based testing. And there's others too, but these are the four I was kind of mentioning. And so the problem that I've noticed working on different teams is that you start to develop unsustainable testing practices when you start to hold one of these over the others. When you start to hold code coverage as the main thing that matters. You can have a 100% code coverage test code base where you've unit tested everything and all that, and still have a whole lot of bugs in production. You have to do a combination of all these things in order to have a sustainable testing practice. So, and for the purposes of this talk, I'm going to focus on the last one, model checking and property-based testing. So the model checking domain is quite broad. There's a whole lot of different meanings to this word. And so there's things like TLA Plus for formal verification, created by Leslie Lamport. And there's things like design for kind of building out like a model of your software and checking it there and then generating that, taking that model and being able to generate code in another language. And things like Concurrent for Erlang and Elixir for being able to check for concurrency errors in your code. And there's things like quick check, proper, and stream data, which are kind of a subset of model checking. And so, as I mentioned in the last one, I'm going to be focusing on the last ones, and specifically prop check, which uses proper behind the scenes. And as Jose mentioned in his keynote yesterday, Fred Hebert has a book which is excellent. He's, it cut off over there. But anyway, Fred's name is supposed to be at the bottom. And so he goes into more detail than I'm going to go into today. And it's an excellent resource. Fred's a really entertaining entertaining writer. And I wanted to mention some terminology that we use, that we've been trying to kind of get ourselves on sync at Toyota Connected. And anyway, want some common terminology that I'm going to refer to in the rest of the talk, like testing levels. There are unit, integration, system, and operational testing levels. And I have the box style kind of up there. For white boxes, you have full access to the code. You could modify like a variable, for example, inside the function, or you can have a mock or a stub or something like that. And then gray box are the kind of integration things where you may like inject something into the database, but then kind of do more of a system level test after that point. And then system are black box tests where it may not even be written in Elixir, but you may be writing a test suite that tests maybe a legacy system or something that you want to be able to replace. And then operational tests are non-functional tests. They are ones that have to be performed by humans. For example, if you work at NASA and you're building a rocket, you can have all the simulations you want, but at the end of the day, you got to go fire the rocket. And so that last one is the hardest. So it's that column where about automatability, which I'm asserting is a word, is the ability for it to be automated. And so the operational tests are very difficult to automate. They involve humans. Versus the unit tests are very easy to pick up. We can all get them. We know what to do. We understand how to write them. And but the problem is they also have the lowest value. And so the value is kind of inverse. Like a bug that happens, like for example, if you go through all the simulations on that rocket and all these things, you've done all these things along the way, and then you finally go test it and it blows up, like that's where you should have found that out earlier in the process. That's where you're going to find your most valuable bugs. And so some additional terminology that has been helpful to me while working at Toyota Connected are some things that we've kind of borrowed from the Japanese culture that they have there in the company, in their production line. And those include, and we try to apply those things to software development, and those include things like jidoka, which is kind of roughly translated as automation or automation with a human touch. You can't forget the human part of software testing, because at the end of the day, like I mentioned, bugs are subjective. They involve like if you have a logical bug in the way that the business logic is, the computer's not going to be able to tell you yay or nay on whether or not that's a bug or not. There's Kaizen, so no matter what state your current test code base is in, you can always, so roughly translated, it means continuous improvement. There's little things that you can be doing to help improve these things and make things better, both in the community and your own, the projects that you're working on. And then one of my favorites is Genshi Gamutsu, which the two words there in Japanese are actual place, actual thing, or go and see. And this is something I think we sometimes forget as developers, is we're so busy, programming and, hey, the test suite passes the way that I think it should work. You'll learn a whole lot if you just go out and watch the customer use the system that you built. It's an important thing that I think we sometimes forget. And so, those are those three kind of concepts that we use a lot within Toyota Connected, and I think will help as you're considering how to improve your testing. The other thing that we use internally is the PDCA cycle or the OPCDA cycle, where you observe, plan, do, check, and act. And there's also called the Deming cycle, and there's one that the Air Force uses. It's the same kind of principle. Basic idea is that you do small little improvements using that Kaizen principle, the continuous improvement principle, to improve your quality. So don't feel like the things I'm about to show you related to stateful property testing is something that, I got to do it everywhere. No, you can pick one small thing and make it a little bit better and a little bit better, and you yourself are going to become better, and your quality is going to improve, and your team's quality is going to improve. And anyway, so that was a bunch of terminology. Back to why we're testing, is to find bugs. So just want to make sure that I hadn't lost anyone. So I'm going to be going through kind of the different testing levels and showing some examples using property testing at each of the levels. So for unit testing, this is the easiest to understand. We should be able to pick it up pretty quickly. I have a function here called smallest that just takes a list and iterates through the list recursively, and it returns whatever the minimum or the smallest element in that list is. That's all it does. And pretty simple, pretty easy to understand what it does. And here's how you might call it. Where I pass in a list of 1 and 2, I get back 1. Or atoms are greater than integers in Erlang, so if I pass in A and 0, I get 0 back. And it's pretty easy to understand that. So here's why we might run a unit test for that, where we have these kind of static tests that we've come up with. But as I mentioned, so I want to talk about model checking. And so in order to start off with that, you have to come up with a model. Or another name for this, which I learned from Fred's book, is an oracle machine. It's something that is so simple that models what your system is, that it can't be wrong. And so an example of that is if I sort a list and then I grab the first item off of the list, then I obviously have the smallest item in that list. This is not as efficient as my implementation, in my main implementation, but this is an oracle machine. This is as simple as it can get, and there's no way that it can be wrong, or hopefully. And so I've modified our test here, so instead of just checking for the static values on the right, I'm checking to make sure that my system matches the model. And so that's the only thing I've changed. And then to do property testing, all you do is that. So for all non-empty list of terms, I verify that my function matches my model. So this principle is the one that we're going to be using in the next couple of steps, which it's going to be a bunch of code. Don't get lost in the code. This is the simple principle that's driving everything behind the scenes. So for integration tests, I wanted to find a system that was obviously broken concurrently, that had a problem. And so I tried to think of it's because most people seem to use like a cache or something like that as an example during this phase, but I wanted to find something that was obviously had some issues in it, concurrency-wise. And so I tried to find something that was in the real world that I could model, but I ended up using something from the wizarding world. So in Harry Potter, there's this concept of a pensive. And I realized after I wrote all this code, talked about it with my wife, who loves Harry Potter, and I realized we disagree about how this works. But anyway, this is the way I thought it worked. So you have this pensive, and you have this kind of library or shelf of memories that anyone can go store memory on that shelf. And you can load a memory into the pensive, and then you can relive the pensive, and then take it back out and put it back on the shelf. And so technically, between the time that you've loaded it into the pensive, someone else could come in and relive that and have put it back on the shelf before you could have, you were able to see that memory. And so the implementation doesn't actually matter. You shouldn't have to care about it. It's in that GitHub repo I mentioned. It uses a gen state machine behind the scenes and a supervisor. But the operations you can do is you can start the pensive, and you can store memory in there, and you get back a memory ref or a pointer. And you can load the pensive with a memory using that memory ref or the pointer. And you can relive it. When you relive it, it kicks whatever memory had been loaded in back out, and it's back into the empty state, and you can stop it. And so the states that this thing is able to be in are the stop state, which can move to the empty state. Empty state can move into a loaded memory state or back to the stop state. And then a loaded memory can be kicked back into the empty state or back all the way to the stop state. And it's fairly simple, yeah. Oh, and then plus the data that actually stores the actual memory, so the shelf that's there. And so let's go build our model. So for our model to be deterministic, I don't want it to involve any processes. I don't want it to involve anything other than just kind of mutating its own state locally, just in a map or a struct or something like that. So that's kind of what I did. A struct that has a state, and then just the data, a map of memories. You create a new one. If you start it up, it moves from the stop state to the empty state. If you stop it, if it's in any state other than stopped, then it'll stop. Store can write memories to the pensive's kind of memory data at any point. Loading a memory in can only move from the empty state to loaded. If it's already loaded, it should return already loaded, like an error. And then same thing with relive. It has to have already been in the relive state, in the loaded state in order for it to return a memory. Otherwise, it just returns error. So we've kind of got our model in place, our deterministic model. And we can use that to write kind of an integration test against the system that starts up the app and starts our model. And we kind of lockstep the whole way, making sure that our model and our system the whole way along. So we've started both of them, made sure that we got a PID back from the system. We store a memory in, and we load a memory into both, and we check at the very end that when we call relive on both of them, that they both match. So they're kind of lockstep with each other the whole way. And we stop and then tear everything down. And so this is kind of a happy path kind of test, which is great, but this doesn't really help. I mean, remember the original goal of testing is to help us find bugs, and so we haven't discovered any bugs. We've just written the same thing twice, one involving maps and one involving processes. And so what we can do next for system testing, I'll show you why I'm calling it system testing in a minute. Using something called prop check statum or proper statum, it's this state machine thing that's built in. Using that same simple idea from the beginning where we're generating a non-empty list of terms, we can generate a non-empty list of commands that we can do against the system and our model. And it does this by having two modes that it operates in. It first operates in a symbolic mode where, so these are actually the callbacks that you would have to implement on your module if you were using this. Returns an initial state which gets put into the command callback. The command should return some kind of command, so load, or relive, or start, or stop, or whatever. And the precondition callback checks whether or not that command is allowed to happen or not, based on the previous state. So if load is being called while it's in the stop state, that's not allowed to happen. So it returns false, it goes back and tries to get another command. And so it'll generate a list of kind of abstract commands that it's going to try to actually run against the system as a result. And next state actually modifies our model if the precondition passes. So then it actually goes through and does what's called dynamic model state, where it actually runs the command against the system, and it has an additional callback called postcondition that checks, the result of the system. So I ran start, did I get a PID back, for example? So if that fails, it goes into the failed state, and you can have it print out a nice report. So this is so what I did was I wrote out my test, and I forced the postcondition to fail on the reload call. On the relive call. And so this is what you might get printed back out. It shows, so remember the list of commands would be random. And so what it does, it'll shrink down. It'll try to take commands out of the sequence until it's able to produce the same fault or the same error with the minimum number of commands. And so it'll show you, like, if you have some kind of shopping system, for example, if I log in, I add a thing to the cart, I log out, and I log in again, and I check my cart, there's nothing there. Like, it should have stayed there, but it's gone, for example. So here, if we start up the pensive, we store memory in, we load and then relive, then it shows at the bottom that the post condition was false, because I forced it to be. And you'll notice here, so during the abstract state, it doesn't actually use things like the PID. It uses symbolic variables. So like var1 is the output of the first command that is being used as the argument list for the second command. So it generates this whole plan that it's going to go do using these symbolic variables that get replaced when it actually moves into the dynamic mode. And so anyway, that's kind of how that works. And then the state there, I replaced the PID with an atom, P, for right now. It was hard to make it look nice on here without it like running over. And you can also inspect the history of what the state was at each step during the process. And so you notice on the left, I have nil there. So because the way that I built this was I have on the left the system and on the right the model for the state that gets returned from initial state. And so on command here, so if I'm in the stop state, the only thing I can return is start. And I'm not going to show you all the different commands. You have to go look at them on the repo. And our precondition just returns false if it's in any state other than stopped. And our post condition checks that the system returned a PID when start was called. And then next state is what modifies our model. And so it's a lot, like when you actually go about, I encourage you to go find something that you've built in the past, maybe a legacy system or something that you feel like you understand how it should work, and go build a stateful property check for it. Or stateful property test, because it might surprise you that you don't understand your system as well as you think you do. And it's very simple. Just you should be able to identify right now what commands or what calls you're able to do against your system. And so this is what the actual like XUnit test would look like. And if you remember from the beginning where you had like for all non-empty list of terms, all I'm doing here is for all commands, and I'm passing in the model that I built, and then I run the commands. And there's also two functions for parallel commands and run parallel commands. And so you can use these tools to help kind of find, it's not quite as exhaustive as things like Concurrent or other systems that are out there, but it's pretty good at finding some of these concurrency errors that exist in your system. And then at the very end, we just check to make sure the result was okay. Otherwise, we have like a win-fail clause that'll print out a nice report otherwise. So when you run mixed tests, this is how it looks. It shows, I have mine printing out like the percentage of which commands ended up being called. And you'll notice that it's doing start and stop a whole bunch, because those are kind of the initial states that it could be in. And so just because everything's weighted equally, like it's just kind of iterating back and forth between those two. So you can use a technique that's built into Proper called frequency or weighted union. So this is there were actually some concurrency errors in that initial model I showed you, like where one person loaded it in, and another person was able to get in. So replaced people with processes, and it found the error. So I had to kind of expand out the test a little bit, where I'm printing out which state it was in on the left, and then also like what command was attempted. So in the empty state, load known was attempted. And then also load known was attempted while it was already in the loaded state. So I actually checked, did I get the right error back if I was already in the loaded state? Anyway, so that's kind of what you can do there. So I kind of shaped it to where like if I like don't prioritize start and stop too much. Like try to get down to the other states earlier. And in the GitHub repo, I have a little bit meatier example called Share. So at Toyota Connected, the main thing that we're building right now, at least on the team I'm on, is a car sharing application. So this is a very, very stripped down, kind of simplified version of that. You have drivers, you have vehicles, and you have reservations. Drivers can only make a reservation if they're approved, and two people can't have reserved the same vehicle at the same time, and stuff like that. So it uses Ecto and Postgres and GraphQL, and so all of the system level tests are done over the GraphQL adapter, which means that I just swap out which transport I'm using. Right now I'm calling them locally, but I could swap that out to be over HTTP or over WebSockets or something else, and I don't have to change my tests at all. So the model that I built and the system that I'm checking, once that's put together, you can kind of point it at whatever you want. You can point it at the integration level. You can point it at the system level. You can point it at production if you want to test production. You can point it at a legacy system that wasn't even written in Elixir. And so, I don't know. I found this is a very powerful tool to kind of help not only like verify or like help you understand whether or not you understand your system, and then also kind of accomplishes the same goal where test suites are supposed to be long-lived. This is something that if once you build it out, the only time you're going to have to add a new command is if you change the properties of the system. If you're just changing the implementation details, you don't have to go change your tests again. They should still pass. And so, and then I mentioned really briefly about operational testing, some of the stuff that we do within Toyota and Toyota Connected. So the main product that we've launched back in July is a car sharing application in Hawaii called Hui. And so a lot of us had the opportunity to go out and actually like see customers actually using the product in Hawaii and how it was being used. How was it being used operationally by the fleet coordinators, behind the scenes and our business partners. And so, these were all photos that I took either while I was in one of the Hui vehicles. I wasn't driving, by the way, in those bottom two pictures. I was in the passenger seat. But, being able to watch, if you want to find bugs, go do this. Because you realize, oh, well, that part does not work the way that I thought it would, because you've gotten so ingrained with the way that, like, I click this, I do this, and there it works. Then you watch someone who's using it starting out from new, and you may realize, like, oh, that's a terrible user experience, or they clicked this thing. Why would they ever click that thing? But it broke, and anyway, like, it'll help you identify the properties of your system, and also which parts that your customer or your client holds as the most valuable. The things that you might consider the most valuable may not matter to the customer. So anyway, so in general, I hope that was the main point that I tried to get across. I tried to show you one tool that you can use to kind of help do some of these things, but the main goal is finding bugs. Use whatever kind of technique or discipline or tool or whatever exists out there to help you find bugs. The value of property testing, which is why I think sometimes it's kind of hard to show others why it's valuable, is you find the bugs while you're writing the test. You don't find them after it's written, and you don't get to see what was fixed while you were walking through all the steps. For example, on the car share thing that I have in this example repo, I found a deadlock condition, like in Postgres, where I had a transaction going and someone suspended a driver at the right time while it was also checking that driver was approved at the right time. Anyway, there's a deadlock condition that might have showed up in production, after like a few months, and you're like, well, what in the world was that? And then you just kind of forget about it until the next 2 months. Or you get more people on the system and they start happening more often. And so, anyway, that's the main point. Use whatever tool you need to be able to find bugs. And that's it. Thanks. Okay, so I guess we got a few minutes for Q&A, if anyone has any questions or answers for me.
So the property-based testing feels to me a lot like fuzzing, maybe like a more white box version of fuzzing. I'm wondering if it's also mutational.
What do you mean by mutational, I guess?
It takes the generated input, like for example, say you have a really long string, and then will randomly flip bytes in it or flip characters in it.
Oh, okay, yeah. So some of the way that the generators work is I think the term that Proper uses is like generational, where it uses like the previous thing to kind of drill down. But you can kind of tune. So in Fred's book, he talks about like how to build your own custom generators and how to tune the way. There's a thing built into Proper called simulated annealing, where you can kind of shape the way that the data is being generated and stuff like that. But he also talks in the book about fuzzing and how on the generator side, it looks like a whole lot like it's fuzzing, but on the shrinking side is where it actually kind of differentiates itself. The way that it's able to take, like, maybe it sent a megabyte worth of a binary into the system and it crashed. was it the big binary, or was it the fact that you had the word, the letter A in there? And so it's able to condense that down and say, like, this made it crash, A also made it crash. So does that kind of answer your question?
Yeah. Also, since it's generational, how do you have confidence in it, knowing that you've generated enough cases? Like, for example, when I'm fuzzing, I might fuzz Python for days, and then eventually I run into a bug.
So let me show you back on this screen. That's actually a common, let's see if I can get over to this screen right here and scroll over. So there's these options that you can pass in right here on your test. And so a common thing that I've done in the past has been, once I kind of get my model in place, I'll bump that 100 number up to maybe 100,000 and have it run for a couple hours. And I mean, initially, once you start out, you're going to find bug after bug after bug after bug. And eventually, they're going to stop happening. And it's up to you to decide when because, I mean, you can't test everything. So you have to kind of give up at some point and say, like, it's pretty good. So.
I was wondering if you had any opinions on mutation-based testing, where the tester actually goes and modifies your code base, and then you should expect your test suite to fail.
Does it help you find a bug? I mean, like that's what the metric kind of is.
Right.
If it does, then yeah, it's great. If it's not, I don't know. In my mind right now, I'm wondering like what you're checking.
Numerical validity. In my case, it's scientific background.
Oh. Sure. Yeah. Yeah. That could be a good technique to use.
Thanks.
Hi, I'm curious whether or not you're using UX designers that might be doing user testing as part of the design process, maybe ahead of writing code, and whether or not those test cases inform what you're doing, or do you see this as sort of a separate sort of an effort to understand the requirements?
It's so the way that it's worked on the team that we're at Toyota Connected is we do all of that, and so a lot of these things are caught during the customer kind of UI UX kind of design feedback loop that's there, or the PDCA cycle that's there. But there's some things that that just slip through, or that you don't really realize until you're actually like standing there trying to reserve a vehicle, for example, and you're in a parking garage and you're like, oh crud, I don't have cell service. So like there's all kind of those kind of things come up from doing both, I think. Does that kind of answer your question? Okay.
Great talk. I have a quick question as far as, I'm a big proponent of using the right tool for the job, and I feel like there's a lot of talks out there right now about model checking and property-based testing, and I'm hesitant to always, hit everything with it as far as using it as a tool. Can you give a good example of maybe where model checking / property-based testing would be a bad idea, or maybe a route?
Yeah. So Fred has a whole section about this in his book. And he says it's a hard question to answer, because it takes just experience with knowing this is overkill. I don't need to be doing this with this piece of the system, for example. I like to use frequently asked questions as an example. If you have an FAQ section of your site and you're using property testing, it may be overkill. I mean, you may be able to just get away with a very simplistic just test there. There's not going to be a concurrency error there. It's frequently asked questions. So it's a hard question to answer, I guess, but it just takes time. You're going to realize at some point when you've over-tested something. So.
Thanks.
Mm-hmm.
Anyone else, guys?
Perfect. Well, thank you.